Okay folks, welcome back. Here are some devices. These may look familiar to you. Okay, in my last video on induction heaters, I said that was the last video I was doing, but I actually lied because I came up with a new driver that seems to work even better, and it's in this box. See that red light? That's an overcurrent light, and basically it's sensing the current in the coil, and if there's too much current, it comes on and shuts off feedback. That's what you're seeing. So as you just noticed, the light went off when I put a load in the coil. So now I'm going to remove the load and look what happens to the light. It comes back on. Now if I put the load back in, the current will start back up again. And heating of the load resumes, as you can see here. Now here's the schematic, and I'm going to post a link to it in the description on how this setup is made. But it basically has a startup oscillator which gets resonance going, and then feedback takes over. Now in this experiment, I'm running it at much higher power levels, and as you can see, you can easily melt copper with it. And here I have 2 pounds of iron that's melting. Of course, the current draw is a lot greater when you have iron as opposed to copper. And here's some more pictures of the iron melt. Now, I did design a PCB, and here it is with all the components on it. So it's pretty easy to put together with the PCB. And in the link in the description, the Gerber files will also be there, so check those out. I also made a PCB for the gate driver chips, the IXDN inverting and non-inverting gate driver chips over here. So check out the files for that as well. Here's the copper as it's kind of degassing or boiling. It's hard to tell what it's doing, but I wanted to see whether it was boiling, and so I filled a test tube up with water, and I placed the test tube right above the boiling copper to see if I could get condensation on the glass of the test tube. And as you can see, that wasn't very successful because it just splattered copper onto the test tube. By adding a little bit of borax into the copper, it can prevent oxidation from happening too quickly. In this experiment, there's the startup frequency. I'm scoping the gates, and as I increase the voltage, you can see how resonance takes over the oscillations from the feedback mechanism. Okay, this is the finalized build, and the bus caps are on the left, those 2 black capacitors. I'm using a more compact cap bank here, which is water cooled, so I can get away with a smaller but higher duty cap bank. So here's some basics on how it works. Here's the tank capacitor. This is 2.6 microfarads. The red and black wires are connected across this tank, and the voltage across this tank then goes to a smaller capacitor, which is 100 nanofarads over here. So to do the calculation, it's 0.1 over 2.6, and just say we have 500 amps in the tank circuit, it comes to 19 amps flowing in the smaller capacitor. Now if we take one of the legs of the smaller capacitor and put a 20-turn ferrite transformer, we can step down that current by 20 times, and so it'll become 1 amp. This arrangement gets rid of the need for a current shunt, which wastes a lot of energy and causes a lot of unnecessary heating. So with 500 amps in the main tank, the 20-turn transformer has 1 amp in it. With a 100 ohm burden resistor across the ferrite transformer, that translates to 100 volts across the burden. The feedback current flowing into the PCB can be further reduced by adding a second 470 ohm resistor in series with the output of the burden resistor, and that reduces the current to about 0.2 amps, which is much more reasonable. This much lower current enables us to pass it through much smaller opposing diodes. These diodes are 9.1 volt opposing diodes, which cut down the voltage from 100 volts and which is clamped to 5 volts by these two diodes here. Once it's clamped down to a lower voltage and current, it then goes to the logic circuitry here. The reason for having these small 9.1 volt opposing diodes is to prevent loss of the 5 volt startup signal, which would short out through the feedback transformer. And that's why these had to be added into the circuit. Without these, there are no startup oscillations to get the thing running. The voltage in the tank is rectified by this diode and stored up in this capacitor here. It has to pass through this 100K resistor first before it stores up in the capacitor. A 20K potentiometer is connected across this capacitor, and the wiper of the potentiometer then connects to the base of a transistor, and this acts as the switch. So here's the base right here. This transistor is basically how current control is achieved. For this build, we use a full bridge of SKM 100GB IGBTs. These IXD inverting and non-inverting gate driver chips are connected to a gate drive transformer, which in turn turn off and turn on the gates of the full bridge. These chips drive this gate drive transformer. You need to find the right kind of ferrite so you have good gate waveforms, and that's important to do. So you have to experiment with different types of ferrites and different number of turns. The output of the gate drive transformer is connected to the gates via these 5-watt resistors and the Schottky diodes, as you can see in this picture right here. The output of the inverter is connected to the coupling transformer with a DC blocking capacitor. Pretty much any value will work. You want around something greater or equal to what you have on your tank. Here's the coupling transformer. The type of ferrite is important because you want a ferrite that can handle medium to low frequencies, and you want something that can handle the amount of power. You want to experiment with different types of ferrites. Manganese zinc or nickel zinc typically work well. These ones work great. What I found is there's quite a bit of trial and error to find the right size and value. For your resonant tank capacitor, one such as this is not recommended as it can't be water cooled. When I tried this out, those capacitors got very hot very quickly. What you need is a capacitor that can be water cooled and specifically designed for induction heaters. This one can handle at least 650 amps at 700 volts, and the great thing is it can be easily set up to be water cooled using these water blocks, as you can see in this picture. For current inrush protection, you need an anotherm thermistor. I've got two in parallel here. So here's the final build. It's fairly compact, even though it doesn't look like it is. But here's my work coil. I've covered it over in glass fiber material so that the turns don't short out with each other. Everything on this setup, is water cooled. The control circuitry, current control circuitry is in this metal box. The current transformer is right here, all set up there. I'm using 50 nanofarads across the main tank to reduce the amount of current that flows. I initially had 100 nanofarads, but I found I could get away with even less. And I actually upped the number of turns on here from 20 to 30 turns on this current transformer. This shunt resistor is 100 ohms, and then the output of the shunt is put across another 470 ohms before it goes into the feedback. So, put a switch on it too, that's really handy. And this whole setup is running at 120 volts. I'm sure I could probably run it at 240 AC. Here's my gate drive transformer. This is inverting or non-inverting gate drivers. So, you know, so it's all together here. Here's my bus caps. And I've got a big old rectifier here, water cooled, to fill up those bus caps. So before, you know, I go any further, I just want to thank Jonathan Creighton for some very helpful construction details and ideas on this project that helped get the thing started. And I want to thank the guys at HVforum, David Neeren and Anders Mikkelsen, for some very helpful suggestions on building the feedback setup. And I want to thank Archangel Tesla Coil for some helpful construction details as well. His idea was to use these big lug screws to connect in my resonance system. So this is the tank coil. So instead of like, you know, physically soldering it, I can easily change out components by using these big lugs over here. So that's it, folks. Hope you found this interesting. Please don't forget to give me some comments, and if you like this video, please don't forget to like and subscribe.